Hello, everyone. Welcome to my lightning talk on eBPF map batch operations. My name is Chris Tarazi, and I've been working at Isovalent for the past 4.5 years. Today, I'll tell you about the use cases and benefits of batch operations, some well-known, must-known gotchas, and how to use batch operations in your own application. First, what are eBPF maps? Without going into too much details, they are data stores for storing key value pairs that allow sharing data between kernel space and user space applications. What are the use cases and benefits of these? Well, they simply allow us to dump, initialize, and clear elements from a map at once, as opposed to element by element. This is beneficial as it can reduce the amount of system calls your application performs to the kernel, which reduces the amount of context switching between user and kernel space. The more you reduce context switching, the better performance your application will have. These next few slides will show the use cases and their corresponding API reference, but I won't go through each one just for time purposes, but these are here for reference. The main thing we will discuss, though, in this talk is the API of these operations, as they look a bit complicated. Skipping ahead. How does Cilium leverage batch operations? The main usage of batch operations is to perform a batch lookup to efficiently measure eBPF map pressure and export that as a metric for observability. In the future, more operations can be converted to use batching besides just lookups, but we will dig into the map pressure metric calculation. So Cilium needs to be able to do this efficiently, and so therefore it uses the batch lookup. Understanding the map pressure is key to preventing issues when operating Cilium. Some maps in Cilium can be modified by both the agent and the data path concurrently. This means Cilium itself can't keep an accurate track of the map pressure. Therefore, we have to use the batch lookup call to count the number of elements periodically in order to compute the metric and then publish it. However, to use the batch lookup, Cilium must provide a buffer to store the keys and values of the map. But how do you know how to size these buffers? This is where we get into the gotchas. The gotchas of the current API is that it requires you to know some implementation details of particular map types in the kernel. We'll dig into case 3 here because maps of type hash tend to be the most commonly used type, but we'll come back to cases 1 and 2 later. So for case 3, how do you know how to size the keys and values buffers when using the batch lookup call, especially on a hash map to avoid the kernel errors, because it can't be too large and it can't be too small, but somewhere reasonable. The gotcha, though, to finding that reasonable value is that these keys and values are a user space buffer, and the size of them cannot be smaller than the largest bucket size of the kernel space hash map. If you do, the kernel will return an error. But what buckets are we talking about? Let's do a quick overview of hash tables to understand what we mean by buckets. Generally, hash tables are implemented using an array of linked lists, also known as buckets, and a hash function. In the kernel, this is no different. Upon insertion, elements are hashed and inserted into a bucket, as we see with key 0 going to bucket 1, key 1 going to bucket 0. When a bucket already contains an element and a new one's inserted, that's considered a collision, and the new element will need to be chained onto the previous, like we see with bucket 0 and bucket 4. Okay, going back to the gotcha of the user space buffer having to be larger than the largest bucket in the kernel space side of the hash map. But how can we possibly know what the largest bucket size in the kernel is? It's hidden inside the kernel. Well, it's basically impossible, but we can do an estimation where we have the square root of 2 times n, where n is the map capacity. And the map capacity here in this diagram is 7, so we have square root of 14, which is 4, after taking the ceiling, just to be safe. In the diagram, we see that the largest bucket size is 2, so we're good. We have a user space buffer size of 4, and the largest bucket size in kernel space is 2, so we're good in this case. In general, The solution to most gotchas is to use the Cilium eBPF library, as it hides a lot more of the API implementation details in the kernel. It removes details of handling the in and out batch correctly and handles the array and LPM map types automatically. These are the first and second gotchas we skipped over in the previous slides. The hash type requires a bit more work, as we have to determine the keys and values buffer sizes, but I've shown you already how to handle that. Um, Overall, the batch ops API is much easier to deal with using the library, especially with cursor abstraction. Here we have an example of doing a batch lookup to dump a hash map. As we previously talked about, we have the buffer size determined by the square root of 2 times the capacity. And notice the usage of the cursor here, which abstracts away all the complicated details in the API. And that's it. Here's a list of resources and acknowledgements. Thank you for attending my talk, and I hope it's useful for you.